Hello, welcome everyone. I'm Xinho Yu, the chair of RMIT Professorial Academy, the host of this event. So firstly, I would like to acknowledge the people of the Kulin Nation on whose unceded lands we are meeting today. I respectfully acknowledge their elders, past and present. So today we shall hear from distinguished Professor Ma Qian about the connection between metallurgy and nature, a fascinating topic of interest to many of us. So this lecture is actually part of the activity of the RMIT Professor Academy. This academy is consists of RMIT's distinguished professor. We play a particular role in the university in terms of promoting the university, in terms of advocating changes for the university, and also advising university on future directions and opportunities. So before we start, let's just go through some housekeeping matters. So this is a team live event. So you will not be able to ask a question directly to the speaker. So what you should do is please post your questions in the Q&A sections. So at the end of the lecture, I will pick up those popular ones, ask the speakers until the time is run out of the lecture is finished. So let's just start the lecture by introducing the speaker. So distinguished Professor Ma Qian is the Deputy Director of RMIT's additive manufacturing. He published extensively, including 290 journal articles, one monograph and 3 edited books, and he was regarded as a highly ranked metallurgist. He is a fellow of American Society for Metals International and currently serving on editorial board of well-known journals such as Acta Materialia and Scripta Materialia. So without further ado, please join me to welcome Mao to deliver his lecture. So over to you, Mao. Over to you.
Oh, thank you, Zing, for the introduction. Let me just go to the able to see my full screen. Yeah. Yeah, I hope everything works well and go to the full screen. Okay, good afternoon, everyone. Thanks very much for coming to this lecture. My name is Ma Qian, and a few words about myself. I finished all of my degrees at the former Beijing University of Iron and Steel Technology. From the name, you can guess that the university at that time was focused on metallurgy. And then after finishing my PhD in 1991, I joined Tsinghua University, first as a postdoctoral fellow and then as the faculty member. I was at Tsinghua for almost 4 years. And after that, I left China at the end of 1994. Then I visited Japan, Singapore, and then came to Australia in 2000. I joined the University of Queensland with the cost of CRC. So from the completion of my PhD, I've been doing research on metallic materials. So I'm a metallurgist. I was trained as a foundry metallurgist. I joined RMIT in 2013 and almost 9 years at the end of 2013. So in Australia, the University of Queensland is still my longest employer. Next year, RMIT will become my longest employer. And today, before I discuss the connection between metallurgy and nature, I still need to briefly discuss the scope of metallurgy, because the metallurgy, the term has its implications have continued to evolve. I think the metallurgy considered in this talk will still mean extracting metals from ores, but would also include the science engineering of metallic materials at different length scales. Would include the design and manufacture of novel metallic materials. In my presentation today, I would like to go through these few topics. That is, who discovered metallurgy on Earth? Who made all the metals we know? And I'll give you a few examples about the connection between nature and metallurgy and different lab skills. Then I'll conclude my presentation. And then we'll have a few 15 minutes of discussion. So as a metallurgist, and I was curious to know discover metallurgy and where all the metals we've been dealing with come from. This is the motive for myself. And I hope you will appreciate my motive. And this presentation or this lecture today is about the general science. It's not about the in-depth or deep science. So it's more about the connection between metallurgy and nature from a personal view, and this is one of my favorite topics. So who discovered metallurgy on Earth? We know that metallurgy has been critical to our civilization, and our modern civilization began from the metallurgy. So I would like to show you this picture before we answer who discovered metallurgy. This is the Turkey pavilion at the Expo 2010 Shanghai, China. Fantastic design. Would I like to draw your attention to the design of the outer wall of the Turkey pavilion, which has a lot of implications. I'll show you in the next few slides. So this area or this place is Kadıköy. I'm not sure how many in the audience know this place in Turkey. It's a very important place in the history of metallurgy and the civilization of human beings. Let's look at that. So this is where the Kadıköy is in Turkey, and that's Turkey. And this Kadıköy is the World Heritage Site, and due to its critical importance in the civilization of our history, the history of our civilizations. And Kadıköy is probably the largest primitive city settlement we know today between the so-called New Stone Age and the Copper Age. So this is the site of the settlement, and from this layout of this settlement, you can understand that where this design or inspiration came from. Yes, the design of the outer wall of this Turkey pavilion is from the layout of this Kadıköy, the settlement. So this is not part of the entire story, and I put in a picture here. This is the copper bead discovered in this Kadıköy in Turkey in that settlement. And this picture is the promotion picture used by RMIT for my lecture today. And I'll explain this picture first. We have the same length scale. The scale bar is 1 millimeter in each picture. Now this is a hollow titanium tube printed by one of my students at the RMIT Center for Additive Manufacturing. We put the song inside, and the inner diameter of this hollow titanium alloy tube is less than 1 millimeter, is 0.85 millimeter, and the wall thickness is about 0.3 millimeter. So this is the image. This is the hollow tube, titanium tube we printed today. It may represent the additive metallurgy, the current status of additive metallurgy today. Now this one is the copper bead discovered in that settlement, in the Kanahoyuk settlement, and it's highly pure. Because it's high purity, which is absolutely didn't exist in nature, and people, researchers attributed this and to the birth of the metallurgy, and but they were very cautious. They used the word "seemed" to point to the birth of metallurgy. The reason for that is there's an argument about the high purity of this copper bead. And the argument is that this could be the consequence of a big domestic fire, where the extreme heat of the fire has extracted the copper from the high purity copper ores. For example, reduce that by from this carbon, this charcoal, this timber, and this is possible theoretically. And if there was a domestic fire and there was intense heat, then this reaction is quite possible. So they were unable to exclude this possibility. So therefore, and it seemed to point to the birth of metallurgy. So that's the conclusion, or conditional. But anyway, this is regarded as one of the most important hard materials or copper materials which point to the birthplace of the metallurgy. So another one, so another birthplace is Iran, and I'm just going to show just one picture. This Iran and all these areas, this show the smelted copper. It's always related to copper and cold worked copper, and also the mining districts. And so these areas, the collective evidence, it suggests that Iran was very advanced and 6,000 years ago. So apart from this Turkey, this Kanahoyuk, and the next most likely birthplace of metallurgy is Iran. If you are interested in this, probably you can look a bit more about this history, metallurgy before this 4,000 BCE in Iran. I think that's these are the two most likely birthplaces of metallurgy. So we put everything together, and we put this copper bead, we put this settlement. Yes, the theme of the Turkey period at that time was the cradle of civilization. It is, and that's very important aside that Kanahoyuk. I think if you have a chance to visit Turkey, I strongly suggest that just give one day to pay a visit to this area, particularly if you are interested in metallurgy. So, and who made all the metals we know? I think this is the next question. This is interesting, and we are metallurgists, and we know that metals are extracted from the ores, and so the answer looks pretty simple, pretty straightforward. In fact, it's not. Now we look at earlier we discussed copper, and then we look at gold, and gold is the second metal used by human beings, and also it's another one. Its origin was unclear until 2013. When I said that it was unclear its origin, which means that gold should not exist on Earth, as simple as that. So that's physics view, point of view. Where did it come from? And I used this word in one of the earlier slides, and another name, simpler name, is called Copper Age. This was used in England, which means about 4,400 to 4,000, nearly 5,000 years ago, and in mainland England, and the metal items of copper and gold appeared together, and and for those who don't know Australia very well, and in fact, the heaviest, largest gold nugget was discovered in Victoria, Australia, and a long time ago. This is a replica of that gold nugget. This good name for this gold nugget is called Welcome Stranger Nugget. So that's the gold, and Australia is proud of this very the largest gold nugget. Is a miracle.
Excuse me, Mark. Can you lift your voice a bit, louder, because some of the listener found it difficult to to listen. It's a bit low, I think. Just a bit closer, I guess. Yeah.
Is this better?
Yeah, I think so. Yeah, that's better. Yeah.
Okay, I'll do this one. Yeah, and okay, I think we look at the gold, and gold is the second metal used by human beings, and as mentioned earlier, its origin was unclear until 2013. And this picture shows two editors from Scientific American.
Excuse me, Mark, we just couldn't see your face now. So yeah, you just speak louder, I guess. Yeah, that's better. Yeah, that's good.
Give me, I think it's give me a second. I change the position, and
yeah.
This then would this work
Yeah,
better?
I think this is good. Yeah, this is good. Yeah.
Okay.
I think it's good. Yeah.
I change the position in my office.
Yeah.
Okay.
Yeah. Yeah.
Okay, thanks Zane for the reminder. Yeah.
Yeah.
So before we look at the origin of gold, and this interesting YouTube video, and these two gentlemen, they're good scientists from Scientific American. Scientific American, you may know that is probably the most prestigious popular science magazine. It's very influential. Both gentlemen wear a lot of gold. It's very eye-catching. This video was made shortly after 2013, and you can see that the neutron star collisions create gold. And the reason for that is, let's look at this one. And I show this picture to illustrate this. And this was discovered, confirmed only in 2013. Gold and cannot be created within a star, according to all the physicists. And this its formation, its creation requires a more radical event, like the short gamma ray burst. It's GRB. There might be some jargons here in this next few slides, but not many. And the observations of this GRB, this gamma ray burst, was confirmed in 2013. And this provides direct evidence that gold resulted from the collision of two neutron stars. So you can look at this website. There's a lot of story about the origin of the gold, but this was accepted now, and it was very, very interesting. We know gold, so we seem to know gold so well, but not everyone is aware that gold should not exist on Earth. And then we look at another metal, which is lithium. And lithium is interesting, and it's a light metal, and many of my colleagues and myself have been focusing on research on light metals. And lithium is a light metal. We know its critical importance for the battery, and in fact, lithium and also was created by the supernova of similar to neutron explosions, also from the universe. And I'll mention that briefly later on. There's most of the lithium and is created this way. There's only probably a trace amount of lithium existing in the beginning, according to the physicists. And if you are interested, you can visit the website of the National Astronomical Observatory of Japan. That's a very official website there. They list all the story and the discoveries. And the origin of lithium was made clear by 2015 due to this publication in Nature. So it's not a long time ago, similar to the clarification of the origin of gold. And this quickly show this one. And it's the lithium was fabricated, it was created from the isotopes of the 2 helium and plus the beryllium. Beryllium is not a light metal. And so this is the way whole lithium was created. It's really interesting. It's all due to these isotopes of this helium and beryllium. Just spend a few seconds on this one and the so-called Big Bang theory, and it's good for metallurgists to know what we had in the beginning of the universe. In the very beginning of the universe, essentially, there were only 2 elements, hydrogen and helium. And there are also some trace amounts of lithium and beryllium. Other than that, there was nothing else. So effectively, we could say that in the beginning, there were just hydrogen and helium and nothing else. So everything else was created by explosions. That's it. So if we look at the periodic table, all the metals now, I think, ignore the lithium and the beryllium. These are 2 light metals because, yeah, there were trace amounts of them in the beginning of the universe. But effectively, apart from the helium, hydrogen and helium is everything else. All the metallic materials we know today were created by the explosions of different neutron stars or nova explosions. So that's the theory. I think if you're interested in this one, you can look up more information. And but this is the current understanding. I think we, as metallurgists, it will be useful to know where they came from. That's my motivation. Next one, we look at the connection to nature and the different scales. I would use 3 examples to show the connection from my understanding. My understanding is still superficial, and clearly the connections are numerous. You can look at the connections from different perspectives. So I'll select 3 examples and to share my perspective. The first one is the connection via the Voronoi painting. The Voronoi is named after the Russian mathematician. And before we look at the connection between metallurgy and nature, we look at a few buildings in Melbourne and in China. Now, this one is the Melbourne Recital Center. It's not far from RMIT. It's easy to walk there. This is the Voronoi painting. This beautiful architecture, beautiful building is in South back. So Voronoi painting. This is the Voronoi painting. You have the first impression of what's meant by the Voronoi painting here. And then we have another one. This is even closer to RMIT. It's on the Swanston Street, the Melbourne Swanston Street Winter Garden. I passed by this quite a few times. It's very eye-catching if you pay some attention to this. All the internal structures have exactly followed the Voronoi painting. Quite interesting. Next time for my colleagues and my RMIT Additive Manufacturing Center colleagues, you can walk there and have a look at the design there. It's quite fascinating. Now, that's the next one. And probably the best example is here. You are all familiar with this one. That's the Beijing World Cube for the 2008 Summer Olympics in Beijing, and this is the World Cube. If you look at the design, the painting there is typical of the Voronoi paintings, and this is a beautiful design. The entire art wall, the outer surface, has followed the Voronoi painting. It's quite interesting. And for metallurgists, we want to connect the painting with the metallic materials. If I put this one in, and yeah, if I put this one in, this insert, and this is a magnesium alloy made by casting. We call this EQX grain structure. This is a type of desired grain structures. Each grain is a crystal. Put aside is a single crystal, although it's not always. We have this beautiful EQX grain structure. This grain structure would offer desired mechanical properties. And so if you compare this and this, they are very similar, aren't they? So the similarities are remarkable. Metallurgists, many of my colleagues, including myself, have been trying very hard to create this type of grain structures in different types of metallic materials, by additive manufacturing, by conventional casting, by welding. And the architects have easily done this for us. And this is a remarkable example of connection. And let's look a bit more from nature. The nature design Voronoi paintings, we are all familiar with this. The giraffe's fur that has this beautiful painting as Voronoi painting. Next one, this is more popular, the mud cracks. There's good implication behind the mud cracks. Probably not many of us are aware of this one. I hope you're aware of this one. Behind the mud cracks, we've seen that many places and in many areas. Behind the mud cracks is the Voronoi painting. The other one is the dragonfly's wing. It's beautiful Voronoi painting. It's very interesting. I'll discuss the difference. This is another amazing example. The next example is more interesting. It's in your kitchen. I didn't know that before until I saw the promotion picture for garlic. That's garlic. And that picture had nothing to do, and the author put it there, had nothing to do with the Voronoi painting. But when I saw this picture, wow, I thought, well, this is a beautiful Voronoi painting. In our kitchen, actually, we deal with the Voronoi paintings every day in our kitchen. Well, not everyone takes garlic, but interesting. And you might find other fruits or plants which would have a similar painting. It's really interesting. And all these paintings to be happen by chance. Oh, why nature has made all these paintings? It's an interesting question. I don't think the answer is clear enough. So I managed to compare the difference between these two rules. Let's look at nature's rule for the Voronoi painting. It tends to follow the natural tendency to find the nearest neighbors. May not have only one nearest neighbors, the shortest path, the best fit, and also probably, I think this is also important to cater for any survival needs, particularly for the dragonfly and maybe the giraffe. And for metallurgists, and our rule is simple and was made clear by Gibbs. And that means that the system tends to reach a state where the Gibbs free energy should be minimum under conditions when the structure or the grain structure is created. So totally different rules. However, the paintings are very similar, almost identical. I don't know if there's any answer to the to this painting on the giraffe's fur, or what functions do this painting offer? And for this one, really don't know, no answer. Some of you might be interested to find them out in the future. It's a very interesting question. And well, for metallurgists, we tend to look at this issue from the gypsum-free energy perspective. Now let's look at gypsum-free energy. And so all the people in the audience who studied the material science engineering and metallurgy and all this gypsum-free energy. And the gypsum-free energy, you can calculate your own gypsum-free energy, your body temperature, and your body volume. If today, if you don't feel well, that means that your gypsum-free energy is higher than normal. You should manage to lower your body temperature to reduce your gypsum-free energy. You can calculate your gypsum-free energy every day. Make sure that you keep your gypsum-free energy as low as possible. Then you will be in a very healthy condition. That's my interpretation of this one. And for the gypsum energy, if the gypsum energy is minimal, always has the lowest value, tend to have this mathematically. That's the stable state. And for metallic materials, and I showed this earlier, and these are all the crystals. And the boundary, this was formed by casting, by solidification. And the boundary between them is called the solidification grain boundary. And there are crystallographically, we can well characterize them. For example, like these two grains, that's the boundary corresponding to one of them. And the orientations are different. These are the crystals. However, for this, they are not crystals. And why has nature created all these paintings and has then reinforced the strength of the dragonfly wing? No idea. I think it remains mysterious. But for metallic materials, we can reasonably understand them using the metallurgist rule in terms of gypsum energy. I think there's still mysterious phenomena between them, the hidden links or connection between them. So that's why earlier I said that at this point of time is still superficial. And next one, Voronoi painting, Voronoi design is commonly used for 3D printing. You can make a design using Voronoi painting by do 3D printing. This is a 3D printed part, and this one. This can be called a conformal lattice design. This is another one, and a rabbit and skull. So all these materials can be easily designed today following Voronoi painting, and then we can realize them by 3D printing. So this has become well, I could say an important design method for 3D printing. It's not only for fun, actually for real commercial products. So that's the first example to discuss the connection between nature and metallurgy. Our next one, I think I'll look at the connection via the solidification of water. Now this is a classical example. Metallurgists know this very well. First of all, and we look at the water, how important or the importance of water in nature. In fact, as the science continues to develop from depth to depth, and it appears that the importance of the ice crystals in nature is far more profound than we thought before. A few simple examples. Put the picture of the lightning here, and put in a picture of the moon halo here. So the rain, snow, hailstones, lightning, and moon halos. They are all due to the small ice crystals in nature. Without the small ice crystals in nature, there would be no such phenomenon. In fact, the origin why lightning happens, this was not clear until last year. What's new development? And look at this story. Very surprising. As closely, or what could I say, it's entirely due to the small ice crystals. And this one, I'm not sure. This old saying appears to be popular both in China and in other countries. Google that. If you see the rain around the moon, and then it means that rain or snow will come soon. It appears to be statistically, that appears to be correct. And so the small ice crystals or the solidification of water is very important. To my time, I'll quickly finish this one. And for the type of water, they contain many particles, millions of particles, very small, down to the nano size. For the deionized water, that has removed a lot of impurities and small particles. And then for type of water, the ice crystallization, the formation of ice would probably and -1 or 2 degrees. And this is the -30 for the deionized water. However, if we let the deionized water run through the filters with the size of 200 nanometer, that would further reduce the ice crystallization temperature. If we let this water further run through the filters with 100 nanometer, ice crystallization temperature will become lower again. So, and the lowest temperature that has been reached by the scientists, -48. So by doing so, by letting the water running through the filters, we have removed all the fine particles. So all the particles and the particles larger than 20 nanometers in diameter have been removed. As a result, it's getting more and more difficult for ice to form. That's the removal of dust particles from water. And then the production for artificial rain is very popular, and it's based on the adding particles into the moisture-heavy clouds. We call that a cloud seeding, and the particles introduced is normally less than 3 micrometer. And these particles are silver iodide. And after seeding the cloud with the particles, and there will be easy formation of small ice crystals. And these small ice crystals will keep growing until they become so heavy for the cloud. And then the gravity will draw them fall towards the earth, towards the surface. And if all these particles, these are small ice crystals, during their falling towards the ground, if they meet the warm air, they'll be remelted to become raindrops. They can grow larger to become hailstones, or depending on the condition, it's called warm air flow or cold air flow, and that's the way. And this and the theory behind that is straightforward. That is the silver iodide and the ice crystal. They have the similar crystal structure. They have the similar lattice parameters. So they are almost identical. So, and we do this in the commercial production of aluminum alloys and magnesium alloys. And for example, all these particles, the broad particles are zirconium particles. In the commercial production of a large group of magnesium alloys, we add this small zirconium particle, and many of such particles similar to this. This was nowadays is the most done by the drones. The particles less than 3 micron. Similar here is all 1 to 3 micron. And for the commercial production of the aluminum alloys, we do a similar thing, and a different type of particle is probably called a TiB2 particle, and a few other particles. Their size is similar, and quickly finish a few more. So, and in that, in this here, we look at the ice crystallization. We want to form the crystalline ice materials or ice crystals. And by removing the particles, its formation becomes incredibly difficult. By introducing the particles, its formation becomes much easier. The next one is more interesting. We look at the amorphous ice. The amorphous ice is a different type of solid ice material, and I'll quickly go through this. And in the International Space Station, and the temperature there is, the highest temperature is 121 degrees Celsius. The lowest temperature is 157. And the International Space Station, each day would experience 16 sunrises and 16 sunsets. So the temperature change extreme from 121 to minus 127. And in the outer space, further in the space, the baseline temperature is believed to be this one, very close to the 0 Kelvin. So according to NASA, the scientists believe that although unheard of on Earth, the amorphous ice is so widespread in the interstellar space, in the outer space. So it could be the most common form of water in the universe. So that's the theory, and the theory for the amorphous ice. It's very difficult to make the amorphous ice on Earth. However, the people have made them a few very thin amorphous ice samples by applying high pressure. The green color is due to the formation by the highly pressurized process. And we're looking at this one, and this is the model for the ice crystallization or for the ice nucleation. The substrate material can be any particle, can be metal, and that's the water. And with this process, we call that a nucleation. And this substrate material can be any material, and this contact angle is important. Unless this contact angle is 180, which means that they're not going to be in contact with each other. Unless the contact angle is 180, otherwise, this substrate material, whether it's dust particle or metal surface, will be effective to promote the formation of ice crystals. So like the silver iodide, that has a very small contact angle. The smaller the contact angle, the better the efficiency of the substrate material would be to promote the ice crystallization. And the scientists, in order to do that, and they put the pure crystalline silver substrate and also pure copper substrate to produce the amorphous ice, and they were successful. This was published in 1960, and when the substrate temperature, the silver substrate temperature, was lowered to minus 160 degrees, and then instead of promoting the formation of ice crystals, it resulted in the formation of amorphous ice, a totally different type of solid. So this confirmed the hypothesis that the amorphous ice deep in the space is due to the cold substrates. These cold substrates are really cold. They are minus 160. And recall that in the deep space, and the temperature is pretty low, close to the 0 Kelvin. And so this is the theory for the formation of the amorphous ice. Why were scientists so interested in investigating this? Because significant metallurgy, in order to understand the universe and where the amorphous ice came from, how they formed in the universe. They clarified that. And for metallurgists, that has somehow, in my opinion, led to a major development in rapid solidification. When the temperature is so low, the solidification, which means from a liquid to solid, can happen very quickly, milliseconds. That's called rapid solidification. The rapid solidification technology today is well developed, has been commercialized for many different applications. But this was developed, and this is the first workshop developed was held in 1981 in the United States. The coordinator was the then chair of the Department of the Material Science Engineering of MIT, Cohen. He's very famous for magnetic transformation as well. And this is the first workshop which focuses on the rapid solidification technology. I draw your attention to this. I put in a note, I copy the note here. And at that time, rapid solidification processing was a classified concept or technology. And it should not be transferred to foreign nationals in the United States or abroad without a validated export license. Today, this is a common industry technology. However, at that time, it wasn't a classified technology concept. It's very interesting. This technology was developed to realize rapid solidification or to produce amorphous alloys. I think I'll have a maximum of 3 to 4 minutes, to finish everything. And so this is the very interesting development, and my understanding is that this has largely benefited from here. That's a remarkable connection between the metallurgy and science deep in the universe. And also amorphous alloy, amorphous metals. We have the talking about the amorphous ice, and the amorphous metals alloy, they are not used so widely, but they have played a key role in certain high technology applications. This is one example in the digital light processor. And this is the amorphous titanium aluminum hinges and spring tips. This was awarded the AFM Engineering Materials Achievement Award, and has exceptional resistance to the fatigue. So the last example I would like to share with you is connection through topology. And for those who are interested in additive manufacturing, I think you are very familiar with these 3 jargons: metal lattice materials, architectural materials, or metamaterials. These are the popular names. They are hot research topics in additive manufacturing. So there are many different designs and the topology. This is the unit cell. And many designs, we can combine them together to make a new product. For the conventional metallurgy, we focus on all the material science engineering, or the science engineering of metallic materials. We focus on composition, processing, microstructure. Then we evaluate their mechanical properties or other functionalities. Now then, with additive metallurgy, we add another dimension, which is the topology. So what is meant by topology? These examples might be good examples for topology, and let's go through this one. So these materials, if we assemble them together, they are called lattice materials, metamaterials. They can be made in metallic materials, ceramic materials, or polymeric materials. Very popular name and a popular area. And interestingly, let's look at the connection to nature. I use this promotion picture from China. This is in the botanical garden in Yunnan. This is a very well-known place. They call it Qian by now. I would like to have a little bit and the tourist promotion pictures. This Victoria water lily, I think, is probably known to many people as an amazing water plant. And one water lily leaf is capable of supporting 2 or 3 people. This young lady here is sitting at the central region of this water lily leaf, and this is the beneath the structure, is the lattice structure beneath the water. Another one very similar to the bone implants we have manufactured. So this is for the water plants, and also deep in the sea. This is probably another example for the high strength lattice material. This is called the Venus flower basket. This is really deep in the sea, and it has high strength. This is the lattice material. It's all made of the silicon oxide. Or more importantly, or amazingly, the strength of this porous material, or this lattice material, is more than 4 times the strength of the solid silicon rod. And the fracture toughness is 5 to 10 times the fracture toughness of the silicon rod. It's much stronger than the porphyry solid. It's amazing. So, and I recycle this slide, and we can make all different types of materials, including using the solid strut and the hollow strut. And this is the hollow strut. In the beginning, I mentioned the hollow strut, hollow tube. That's for this purpose, for making this metal material to change the topology. And I'm not here. Many of my colleagues are working on this, including myself. And this is amazing. I think last 3 slides, and they contain a lot of elements. Like this one, the dimension 200 by 200 by 200, and the whole structure contains more than 500,000 little struts. That's amazing. So in terms of that, we need to control the metallurgy and the metallurgical defects, the microstructure, and the analog response to the laser of electron beam. And that depends on the energy source for additive manufacturing. And this, from the light metals to the refractory metals that are being manufactured across the board. So concluding remarks, and I think metallurgy began in nature and will continue to thrive in nature to advance our civilization. My prediction is that the metallurgy on the moon will be coming soon, and be prepared to do metallurgy on the moon. Sorry, Zing, I think I have used a few more minutes.
That's all right. Yeah.
And let me acknowledge the Australian Research Council support to my work on the metal additive manufacturing and additive metallurgy. Many of the examples are based on this. The RMIT Professorial Academy for the invitation and organization, and RMIT Center for Additive Manufacturing. Many of my colleagues, team members, my university lecturers, and my supervisors and mentors, and the authors of various source of information used in this talk. Thank you very much for your attendance and your interest.
So thank you very much, Mai, for the fascinating talk. We have just a few minutes. We got a question from the audience. Let me read. It seems the Voronoi pattern in different fields is formed based on their own rules. Can we find approaches to change the rules and result in different patterns? Is there any example in our modern industry?
It's a wonderful example, and we were on the same wavelength. That's why I put it on a slide to show nature's rules. That nature's rules was my guess. Nature may not agree with me. I feel a bit more confident about that. Let me get back to that one. It's a wonderful question. I appreciate this question, and but I'm not certain that nature would agree with me. I made this guess from nature, but I think for this rule, metallurgist rule, I think that's probably true. And for anyone who's interested in this, or in the giraffe, in the dragonfly, I think it would be extremely interesting and informative to find out why the dragonfly wing need this structure. Are these boundaries just for decoration, or just they help to make the wing stronger, more flexible, and more importantly, or similarly, for the giraffe fur? Why do they have this? And to get back to your answer, I don't know. I think it remains mysterious to me. I think we both need to continue to explore the principles behind that. Yeah, thank you for this good question.
Okay, thanks. I just took the liberty of the chair, right? You mentioned about this, many of the elements in the world was because of the collision, right? You know, the explosion. So you seem to support the Big Bang theory, right? I mean, but is that, I mean, in my understanding, I'm not a chemist, in my understanding, we have 113 element in the element periodic table. Are they the only 113, or you think there could be many more? Yeah.
Well, let me get back to another good question. I think this the debate will continue. And well, I think this Big Bang theory. I have kept reading papers of materials on the Big Bang theory, and over the last few years, I think it was very controversial. Now it becomes much less controversial, and I think now maybe can say that it's the most widely accepted theory for the origin of the universe. And according to this theory, yes, in the beginning there were only helium and hydrogen, and it's interesting. They are the lightest elements. And therefore, if you consider these two trace elements, trace amounts of lithium and beryllium, these were the first four lightest elements. So there were no heavier elements. So according to the theory, and all the other elements were created by the collision of the nova or the neutron star explosion. So that's the theory, and I think that's probably the most widely accepted theory for the time being. It's not my area, and I don't have the wisdom to make any hypothesis or suggestion to that. I just introduce this to our audience, to the metallurgists. My motive was to know where they came from. As a metallurgist myself. Thanks, Zane. Another good question.
Thank you very much. I think on that note, we just need to, because the time is up, we just need to conclude the lecture. So thank you very much, Ma, for the fascinating talk. And thank everyone for participating. I hope to see you at the next lecture. Thank you.
Thank you, Zane. Thanks, everyone. Yeah, see you next time.